Hi everyone. So we have a rough analogy between Coulomb's law and parallel lines of current. One other thing I didn't mention in the last video is that this magnetic force actually depends on the orientation of the wires. So if I have anti-parallel lines of current, if I've got one line going this direction, one line going this direction, the lines of current will repel one another. So similar to how in the electric force we have both a positive and negative charge, this magnetic force actually pays attention to the orientation of the current that's associated, that's generating this magnetic force. Now what we want to do is go from force to field, like we did with the electric force. We want to go from force to magnetic field. We want something that looks kind of like this formula where we've got force equals charge, right? The current is the charge in this case, times a field. The problem is this charge is itself a vector. And therefore the magnetic field mathematically is not a vector like the electric field is. It's something we call a tensor. Now, you don't need to know any of that. Just recognize the fact that we effectively can't divide by I in this formula because it's a vector. And so that means we've got a more complicated situation mathematically. And that's why the magnetic field, even though there's a parallel, it's not a strong enough parallel for us to take everything all the way with the magnetic field. However, there is one thing that's true about the magnetic field, and that is that it obeys something called the right-hand rule. This picture here represents how you should think of the magnetic field. So here I've got a line of current flowing into the paper. The magnetic field is actually circular. It circles around the current. And this is what, knowing that it circles is the most important thing, but there's also a question, well, which way is it circling? Is it going over or is it going under? And that's what the right-hand rule is good for. The right-hand rule, basically you take your thumb, stick it in the direction of the flow of the electric current, and your fingers here represent the orientation, which way that circulation is occurring in the magnetic field. That's the right-hand rule. The left-hand rule is going to give you the wrong answer, right? So you always use the right-hand rule to determine which way to draw the arrows in the magnetic field. But I think it's more important to you have to know the right-hand rule, but it's more important to remember that the magnetic field wants to be circular. In the same way the electric field wants to splay out like that, that diagram where you've got, the electric field is pure divergence, the magnetic field is pure circulation. And that's why I wrote these formulas here. If you remember when we talked about divergence and curl, we had similar formula, but here it's swapped, right? The magnetic field has no divergence. It's all circulation, it's all curl, and this J represents the current density. It's I divided by volume, effectively. And so this is how you represent the magnetic field using that kind of notation. This formula here represents the magnitude of the magnetic field given a source of current. And basically it's proportional to or inverse distance, right? So the farther you get away, the weaker is the magnetic field. The closer you get, the stronger the magnetic field. It's not proportional to r squared, though. It's proportional to r. And that has to do with the fact that it's a line of current rather than a point. But this is kind of the fundamental formula for the magnetic field, in the same way that E equals Q over 4 pi epsilon naught r squared is to the electric field.